first, let's discuss about the graph. What is graph? What are the type of graph which can be discussed in the interviews, and what is their associated logic and all that things. Okay, let's get started. So graph is just like tree, but you have connected components, and that can be anywhere. There is no child-parent relationship. So let's say you have one node, let's say A, and another node B, another node C and D. So if it has a tree or something, it will always have some relationship between parent and child. Over here, there is no relationship. Okay, so such kind of connection of nodes are called graph. Okay, now there are many type of graph. Let's say this is undirected graph. There is no direction that A to B are connected in which way. Now, if there isn't a direction, let's say A to B is this direction. That means, let's say you are representing a flow. From A node to B node, the flow is going, or from A node to B node, data flow is going. So workflow generally is getting represented by a graph. We all might have worked with workflows, right? So in that also, workflow represents the graph, or internally it has been worked as in a graph where you know that after this node or after this object to complete or this functions to complete, we have to process this part or this object like that, right? So if it has such kind of relationship, then it is called directed graph, that after A, you can choose either B or you can choose either C. Once B and C completes, or after C completes, you can take D, and then after D, you need to complete B, something like that. So when there isn't a flow or a direction given, it's called directed graph. Also, it's not always simple directed graph. It can be that you have in a loop. It can be that you have any other things as well, like self pointing, a node pointing to itself as well. Such kind of things also can be there. So let's say over here, there is a loop, right? So such kind of things may be there as well in directed graph. Now there are types in which there isn't a weighted graph. Weighted means there is no weight on this edge. If you see, I'm not defining any weight on the edge, but if I define and weight on the edge, that will represent uh, the cost of traveling from node A to B, kind of on a cost or anything you can mention if you want to understand it. Okay, so that, let's say if I represent the Google Maps via graph, okay, I'll say that, okay, from point A to point B, if you want to go, you have a traffic, let's say something, and because of that, you will get some time. So let's say one factor we are associating with it. Okay, so let's say 10 is in a factor associated with it. So that kind of a structure, when you represent, it's called directed graph, directed weighted graph, and undirected weighted graph. Both kind of things will be there. So we have seen two things: normal directed graph and undirected graph. In the same way, you have undirected weighted graph. So you have a weight on the edge, and you have directed weighted graph, in which you have the directions and you have the weight associated with it as well. That from node A to node B, the cost will be 2 unit, or node D to B, the cost will be 3 unit, something like that. Make sense? So far, it's simple to understand. Now let's understand how to iterate over the graph. There is first thing, and when we'll try to understand its implementation, okay, we'll see that in which way you can implement the graphs as well. So generally, let me give you a heads up that in which way you can represent the graph, and in which way you can start coding for the graph and all the things. Later, that practice, we will use it into our coding as per our need. Okay, so the graph can be represented with two ways. One is vectors or list. People call it as an adjacency list. And another is 2D matrix. Okay, so in which way you are representing any graph, and that will be something like this. Let's say you have a node A and it has a connection B and C. So you just mention in A node's adjacency list, So like any node we define in a tree, it will be something like this. Node, node, and let's say character data for this. Okay, and let's say you are giving, let's say, array list as an adjacency list, and of type node only, of type node only. Then in which way the representation work? A has a connection B and has a connection C. So in this way, this representation works. Now, if it is undirected graph, sorry, non-weighted graph, then it's fine. But if the weights are associated with it, you may have to associate the weight of that particular link as well. Like A to B, the link is 2, while A to C, the weight is 1, something like that. So we'll see how to do that with the adjacency list as well. But let's understand with a very simple kind of a graph. Let's let's say like this directed graph or undirected graph. You can represent it with the adjacency list like this. In a node, you'll have all the nodes references which are connected to it. So if it's in a directed graph, you will have A to B and A to C. And from B, you will have adjacency list in which nothing is there. But from C, you will have adjacency list in which D is there, right? Because there is no direction from C to A. C to A, there is no edge. If it is undirected graph, C to A will be there, right? Why? Because in an undirected graph, A also A, B, sorry, not this one. Yeah, this one, C and D. So in this, in A's adjacency list, you'll have B as well, D as well, and C as well. And the same way for B's adjacency list, you'll have A as well, you'll have D as well, because there is no direction, right? So any kind of a directed or undirected graph, you can represent with adjacency list very easily. Only thing is about the weight. We'll see that. The second way is matrix. What, in which way the matrix representation can be and in which way it will be easy. So matrix representation can be like this. Let's say all the nodes I'm mentioning. Okay, and what I have to mention, the weight on that, if we have weight on that. Let's say there is unweighted graph, there is no weight in that, then we'll just keep 1 or 0, that is there a link between these two or not. Even with the direction also we can do. So let's say first we'll understand if it is undirected graph. So if it's undirected graph, we have a link of A to B and B to A both. So A to B, there'll be 1, and B to A, there'll be 1. So that means there is a link between A to B, such kind of this. Let's say you have undirected but weighted graph. Then you'll have that value into that. Let's say you have on a directed graph. Okay, so in directed, let's say A to B only you can go, not B to A. So B to A value will be 0. B to A you cannot go, but only A to B you can go with 2 unit, then 2 unit directed weighted graph you can represent. Okay, so in this way, all the values you can fill it up, and you can keep this matrix with you to process it for any kind of data processing if you need, right? So there are two ways to represent this. Now, based upon the question or based upon the logic required, we'll use one of those. And it's not like that key. If you are using 2D metrics or adjacency metrics to represent the graph, you cannot solve the same problem with adjacency list. It's just that which is easy to implement, that we will take. When a core logic is very much difficult, let's say, and 2D metrics is easy for you to implement, what we'll do, we'll implement the core logic, and a normal implementation of the graph will do with the 2D metrics, so that the rest of the code is easy. Now let's say core implementation is simple, and to reduce the complexity, if we can use adjacency list, we'll use that, right? So it's vice versa. You can solve any problem with any kind of representation of a graph. It's not like that. It's just about difficulty level, how question's difficulty is, and based upon that you can solve it. Make sense? So far I think you guys won't have any doubt. Clear?
Yes, yes, Dhaval.
Yeah. Okay. So just like as you can see, it's in a parent of a tree kind of a thing. What would be the ways to iterate over it? If I want to iterate over a graph, what would be the ways to iterate over the graph?
DFS and BFS.
Exactly. Just like a tree, right? We have, because in tree also we have only two ways, BFS or DFS. Like pre-order, in-order, and post-order are the part of DFS. Right, over here also it's the same thing. You have only two ways, BFS or DFS. Now if you want to change something into DFS or BFS, it can be the part of DFS or BFS. So we'll see how to use BFS and DFS over here quickly, because it's a very simple thing. Just like a tree, you have to use it, and then we'll quickly see the rest of the things as well with the graph. Let's see. So there are two ways to implement or to iterate over the graph, which is BFS and DFS. Let's say we have taken a directed graph. Okay, with undirected graph, it's always easy. So we'll see if you, whenever we'll see questions, in questions we'll see if it is a directed graph or undirected graph, and we'll try to solve it. Okay, so what you do generally in BFS is you use a queue, and let's say from A, let's say A is your starting point. Then in which way you go? You first put first node or the starting node A into queue. You process it. So let's say it represents the workflow. Okay, then you process this node, whatever it has been given into this node to process, you complete it, and then whatever has been into its connection, that you put it into the queue. Now tell me, can you access both the nodes via matrix, adjacency matrix? Yes. Can you access both the nodes via adjacency list? Yes. So adjacency matrix or adjacency list, that will not define the BFS or DFS. You can use any of the representation of the graph. Okay. So once it is done processing that, you dequeue it. Let's say you print that, okay, that has been done, and then you push its adjacency nodes. So let's say you dequeued it, process it, and then its adjacency nodes you have added into the queue, which is like D and B, and so on. You continue the same process. For D, the adjacency node is C. Now, when you do that, okay, you just have to make sure that the same node is not coming again and again. Let's say you have this kind of link as well. So when you have processed A, you might have pushed B and D into the list. Now, when you're processing D first, let's say, okay, you should not push B again. So that visited phenomenon will be required while you are using BFS, right? That will be required. We'll see if it is required into DFS or not. Now, so far, whenever we have seen tree, in trees BFS, we did not need any visited kind of thing. Why? Because we have unified directions, like from top to bottom. Over here, there is no unified directions if it is a directed graph. So that's why you need to keep visited one. If it is undirected graph, then also you need to keep visited metrics or visited list, that this node has already been into visited hash map or something like that. Why? Because if you have undirected graph like A to B, B to C, and A to D as well. So when you process A, you will push all B, D, and C again. Now, if C and D are connected, let's say they are, such kind of graph is there. If D and C are connected, when you're processing C or when you're processing D, you'll not push any of the rest of the node, which has already been there, into queue again to process it, right? If you push it, then also when it's time to process it, you'll not process it. Otherwise, you'll go into infinite loop. Like you pushed C and D, then for C you'll push A, and then for D, D also you'll push. For D again you'll push A, like that. So whenever you're processing, either you check that whether this node is already been processed or not, or whether this node is already been into the queue or not. So that kind of visited phenomena you will have to use if it's in a directed or undirected graph with BFS. Clear? Fairly simple one.
Mhm.
So in this way, each and every nodes will get processed. Now let's see in which way it can be coded. Let's say, or let's go for the pseudocode kind of a thing. The pseudocode can be in a simplest way. Let's say this is the graph. So now I'm just pointing a graph as an object. So you'll have a graph class, and in that you'll have the structure of the node, something like this. You have a graph object in which you have all the list of nodes and all the list of edges, or list of nodes, or the count also you can keep sometimes. Count also you can keep. Okay, and here will be the representation of as in a sub class representation of the graph. Let's say 2D matrix or adjacency list, anything that you want to keep. In that way, you can easily pass the graph object and process it. Or if you do not want to keep as in a graph object and you want to separate it out, then also you can do. Just let's say one 2D matrix is there, which represents the graph in that way. If you want to do, then also it's fine. Or if it's an adjacency list, so you'll have to use list of list kind of a mechanism over here, then also it's fine. So it's up to you. Okay. And when I say list of list, it can be something like this. You have all the nodes A, B, C, and D. So they should be into one list, that you have this nodes. In A's adjacency list, let's say B and C are in connection. Or in B's adjacency list, you have C and D are in connection. In that way, if you want to keep, then you need the list of list. This is one list and this is also list, right? So representation wise, sometimes list of list is difficult rather than 2D matrix, right? So in this way you can do that. Or a simple other way would be that you create, yeah, I think both the things will be fine. It will be in the same way list and each node will be associated with another node, right? Okay, so in any of the way you can represent, we'll see the pseudocode kind of a thing which can be applied over here. So let Q be the queue and we are enqueuing the starting node, just typical BFS. And then until, and you mark this node as visited. As I said, you have to keep some phenomena with which you are marking that node as visited. Either you can use hash map where node to visited hash map of type node to boolean, node to, let's say, visited one or something like that you can keep. So if a node is visited, you keep one, something like that, right? So some phenomena you are using with visited or not. And then if it is not empty, you dequeue the node, you process it, and all the neighbors of W of that graph, of that node V, if they are not visited, you are putting into the queue. Now, if they're visited or not, you can define it in many different ways. As I said, you can have a hash map, or you can have that structure into node itself. So let's say you have a node in which you have the character data. You have, let's say, adjacency list, all the nodes which are associated with it. And you have the visited flag as well, whether this node has been visited or not. So such kind of thing also you can keep. So for all the neighbors of V into graph, you are just checking whether it's already visited or not, and then you are enqueuing it. As simple as that. And you're marking that node as visited so that again it will not get processed. Simple. Now the same kind of phenomena, if let's say if instead of BFS, if you want to see the DFS, In which way it can be? So we know DFS uses the stack. So either you can use stack or you can use recursion. So let's understand in which way the recursion will work over here. You start processing the starting node, okay, and whichever the first node you find it out, you push it into the stack and you process it. So let's say first you found B, then you start processing it. Then you found E, then you start processing it. After E, there is no node which you can process. So you can come back, and after when you come back, so obviously from A to B you went, B to E you went. Now after E there is no node to be processed, so you'll come back over here as in a recursion, which will come back. Now at B there is no other node which you can push it, just like LVER kind of a thing. Left has been done, then you'll do right thing. Or you'll process the right node. In the same way, one of the node has been done, another node is not there, so you'll again go back, and from A, one node, let's say left, is done, then you'll go for the right one. So the same way it will happen over here. If it has any unvisited edge that you need to check, so for all the connections of A or all the edges of A, you have to process this code. For first, you went ahead and you processed it, you came back, you check whether it's there another one or not, and you go for it. Then you go for D, and then you go for C only. Why? Because E is visited already, and then you go for C. So in that way, you can do the depth first search into. Now if I have to code it, how can I code it? Very simply. Or if I say just a pseudocode, if I have to write down a pseudocode, how can I? Yeah, Anurag.
Well, for this also we need to keep a visited node. Visited.
Yes.
Okay.
Yes. Why? Because as we have seen, like E has a connection of both D and B and C, right? So we should not mark that as a visited every time. Sorry, we should not process it again and again, right?
Yes.
So that's why we need to keep it. There may be some other nodes as well. Let's say P, E is pointing to P as well, and B is pointing to Q, let's say, and Q is pointing to R, and R is pointing to P. Such kind of graph is also there. So the point is, when you went from A to B, B to E, and E to P, let's say, then after P, when you're coming back, you should not process the same edge like D to E, E to P again. E to P has already been visited, so E and P both are visited, so you should not process it further. So that's why you need to keep this visited logic there as well, even if it's undirected or directed graph. If it's undirected, then also. If directed, then also, right?
Okay.
Otherwise, if it's undirected, you'll go into the loop. So that's why if it's directed, then why to process it multiple times? Yeah. So the simple logic can be with a DFS, can be with a stack, and that can be like this, that you use a stack and I'm not using recursion. Why? Because recursion will give me unnecessary, very much huge complexity. I'll push the node into stack. Okay, so let's say I push the node A into the stack. Okay, I'll mark that node as visited, and then what I'll do, what I had to do, if you have seen the process of it, it was like A to B I went, B to E I went, and then as from E there was no other path, I came back from E to B, B to A, and then after that from A I started processing D, whatever is the next available node, which is like next neighbor, right? So I have to iterate over its all the neighbors, right? So my code will be to iterate over all neighbors, correct? I have to iterate over all the neighbors. And what I have to do, I iterate over all the neighbors, I push them into the stack, right? And I come back whenever that value is not present. So let's see in that way. So while stack is not empty, I take the node out, and so obviously I take the node into one of the object, take the node out, and for each and every unvisited nodes, I push them into stack, and then I process it further, right? So let's say A is there, then rather than coming back, I'll process B and D both, or D and B both into the stack. Now I start processing B and I push E into that. Now once there is no node from E to process, I'll complete the processing, I'll come back, I'll complete the processing. Now B has connection D. B has, let's say, the connection D, but I'll see that, okay, it has already been pushed, because whenever I'm pushing into the queue, stack, I'm marking them as visited. I'll not push it, and I'll process rest of the nodes. So in that way, I can do very easily, right? Very simply, rather than processing it one by one, is all the nodes, I'll push it into the queue. So if you see, in that way, I can do. Now, also I can use the stack, because it's also I can use the recursion if I want a different approach. It can be very simply like that. Mark starting point as visited, and for all the neighbors, I call this function again and again. So it will be like this only, but you have to use for each, for all the neighbors, just like over here. Okay. Now we'll see both the kind of representation of the graph very quickly, and we'll see then we'll start taking any of the question, and we'll see the code as well. So the representation, as I was mentioning, it was like this, that the graph can be represented with adjacency metrics like this. A to A, there is no node, let's say there is no age, and B to B, so self age is not there, then its weight is 0. If it's a weighted or unweighted graph, you can mention it as values like either 1 or that weight. Let's say this can be one of the adjacency metrics. The nodes are like A, B, C, D, E, F, G, H, and I. So A, B, C, D to A, B, C, D, I. So A to A, B to B, and all of those have no self age because of that. Now A to B, you can go into A to B, you have an weight 4. Now B to A also you have an weight 4. That means it is a undirected graph, correct? Because if you see, the lower triangular matrix is same as upper triangular matrix. A to B4, B to A4, A to C, let's say nothing is there, so C to A also nothing is there. A to H8, then H to 8, H to A8, right? So it's an undirected graph. All the values are same in upper triangular and lower triangular. So that's why it's an undirected graph. It would, if it would have been directed graph, then it can be like this: A to B4 and B to A null. So that can be some other value, right? So that's why I say it. So the matrix representation works like this for directed or undirected, weighted or unweighted graph. In the same way, if I see adjacency list, it can be something like this. The graph have the list of all the nodes. So the graph object will have list of all the nodes, and each node will have list of all the adjacencies or all the nodes which are connected to it, and associated weight as well. Like A to B and D are connected, then I'll just mark it as B and D are connected. B to A and E are connected. Now, if obviously if there isn't a link like this, then B to A I have to keep. If there is no link, or if it's not undirected graph, then this node I don't have to keep it. That's a simple logic, right? And in same way, I have represented all the other values. Clear so far? I think so far was very simple basics. Now we'll see how you can represent the age, which kind of way you can code it for the adjacency metrics, and then we'll move further with the question. And that can be something like this. So as I said, a simplest implementation, because obviously with 2D metrics it's very easy, but with ages adjacency list it can be a little bit difficult. So let's make it a very simple thing. We'll define an age. A to B, there is an age, right? So we'll define an age as an object, so that adjacency list will have A to D if there is an age, like A to D if there is an age. We'll keep that object into our adjacency list, so that what will happen, we can keep the weight as well associated with it. Over here right now we have kept just the node. So instead of keeping a node, if we keep an age, we can keep the weight as well. So instead of a list of adjacency or the node of adjacency list, I'm keeping the list of ages as an adjacency list. So you can see that I have created a class of age in which the source and destinations are given. I am giving the numbers so that it can be easy to understand each and every graph rather than node object. And the age is defined between source to destination, from source to destination, and also a weight. So if it's in a directed or undirected, it can be defined very easily. Correct? The source is A, destination is B. If there is another object where source is B and destination is A, that means it's in a undirected graph. If it's in a weighted graph, weighted values will be there. If it's unweighted, weight will be 0. So in this, with this representation, we can represent both. Isn't it simple? Now, when you define the ages, now you have to define the graph, because in this kind of way, you have to define a graph where it has nodes and adjacency list. So you define a graph like this, class graph like this. You define a graph like number of vertices, and you have adjacency list. And the list has a type of age, not nodes, as I was mentioning previously. Okay, and let's say you have X number of vertices. You define the number of vertices like this. You create an adjacency list. Initially, everything is empty. So when you define it in a constructor, you define a graph. For each and every node, you create a linked list of an empty thing. And then whenever you want to fill it up, you can create an object of age, and you can put it for respective vertices. So what you're over here, you're creating a normal, let's say, you don't have to create a linked list. You can create an array list as well. Okay, it's a fairly simple, both are the simple thing into Java. In C++, let's say you do not have linked list as a standard library, you can use array list. Okay, in C++, but in Java and .NET, you have both as a standard libraries. So it will be fine. It will be both same. So what you're defining, when you are defining a graph object, and you are just defining a list of vertices, that's it, with the numbers. When you are moving further, then you are creating an object of age, and you're pushing into the ages adjacency list accordingly, right? So you can create an age very simply like this. Let's say the method is like add age. Okay, you are creating an age of source to destination. Okay, and then you are adding it to adjacency list of source. Adjacency list of source, and the first age you are adding. If it's an undirected graph, oh sorry, if it's an undirected graph, you create between destination and source as well. So the point is, this is in the case of undirected graph. You have A to B like this. Then you create two ages, A to B and B to A. That is what I'm doing. Source to destination and destination to source. And both the things you are putting into respective adjacency lists. So in A's list, you'll have adjacency list AB, and in B as well, you have B to A edge as well. That is what you are doing over here. If it's directed, only A to B is there, then these two lines will not be there. Clear? So far clear with the implementation part and which way we can use the code, which would be the easiest way. Clear? I'm not covering 2D matrix part because it's very fairly simple one with the graph. So far clear? Anurag, Harsh, Jose, Karthik.
Yes, sir.
Yeah. Now let's see the primitive some algorithms on basis of which the interview questions can be, on basis of which the new algorithms have been formed. And the basis of these algorithms were as well the basics, BFS and DFS only. Let's see those first. So this phenomenon, this topic is called minimum spanning tree. And what is that? That we will see. What is called minimum spanning tree? What are the main algorithms for that? And when we see the questions, we'll see how the similar kind of an approach of minimum spanning tree is itself is repeating. Okay, so we'll see first what is minimum spanning tree, and then we'll move further. Do anyone have idea about what is minimum spanning tree? If they remember from college time, or if they are preparing right now for the interviews and have read about it, they can share.
With I mean, like with minimum vertices, we should be able to.
Exactly. So what he says is that with minimum number of vertices or with minimum number of edges weight, anything can be the definition of it, with which we want to cover the whole spanning tree. So let's say what it means is this. Let's say you want to cover this whole graph. Then the minimum spanning tree can be that you go from A to B and A to D, let's say, then D to E only and D to C only. So you're not traversing these two edges. So your minimum spanning tree becomes like this: A to D, A to B, and D to C and D to E. That's it. This is your minimum spanning tree. You're covering all the nodes. Okay, the normal definition is you are covering all the nodes. So you're covering all the nodes, but with least number of traversals of the edges, or the weight can be anything, but generally in general definition, it's edges, number of edges. So with minimum number of edges traversal, you're covering the entire graph's nodes, and that is called minimum spanning tree. Now, if you see, there can be some relationship between over here, between the number of edges and the number of nodes. Can anyone guess what will be that? Another minimum spanning tree, if the weights are not associated, then can be like this. A to D is must. A to B is also must. Then let's say B to E you are going, and D to C you are going. This is also another minimum spanning tree. Another one can be A to D, A to B, D to C, and C to E. This is also another spanning tree. Minimum spanning tree can be out of anyone based upon the weights. But is there any relationship between the number of edges and number of nodes in minimum spanning tree? If you see, there is. Check it out. So you guys have to figure it out. What will be the relationship between number of edges and number of nodes in minimum spanning tree? Okay. Let's see. So the spanning tree can be defined as that in directed, undirected, and connected graph. You span all the vertices and you create a subgraph of G such that every node is every node you have traversed and every edge is a part of graph only. Then that kind of a subgraph is called spanning tree. And when you are associating a minimum spanning tree, it says that the cost of that whole traversal, as I said, there can be multiple spanning trees for our previous example. What will be the least weight associated with all, or the summation of all the edges, whichever is the least, that is called a minimum spanning tree, right? Now the point is how to find it out the spanning tree, because as I said, as we have seen, there can be multiple spanning trees, even it's in directed graph or undirected graph. The basic definition is undirected graph as a definition of a spanning tree. Okay, so let's say we are going with the same thing, undirected graph only. Point is, how can we find it out the spanning tree? So let's say if this is the graph given to you and you have to find it out any one of those, any one of 3 spanning trees. How can you find it out? Any idea? Well, any basic logic which comes into your mind that, okay, I want to grow this kind of an algorithm, or any logic which is coming into your mind. So first of all, you guys are understanding the spanning tree, right? And minimum spanning tree. Then we'll move further with this question, that how or what is the logic that currently you are thinking, which can give me this answer.
Can we do a DFS?
Sorry.
Can we do a DFS? I mean,
Yes, you can do the DFS. There's no worry with that. So let's say in this only, you went from A to B, B to E, you come back, then A to D. You after that, D to E is not to visit, right? So you went like this, A to B, B to E, you come back, then A to D you went, then you come back because D to E is not there. So you come back and then D to C is there. So you went to D to C. Now C to E you try to go, but there is no way to go. Why? Because E is already visited. So you come back and then you say that, hey, whatever the edges I have found it out, they are a spanning tree. That's perfectly fine. Point is, how can we go for the minimum spanning tree? Your concept of spanning tree is perfectly fine. So with the BFS or DFS, we can go for the spanning tree. That will give us one spanning tree. With some altercation into the depth first search algorithm, we can print this spanning tree. Now let's think about it, that you got one spanning tree out of all the possibilities. Okay, if you go for BFS, one of the other possibility can be there. Now, how can you go for the minimum spanning tree?
Is that the case that we need to take start node? Means, for example, on the first go, we'll take A as the start node and do a DFS on that, and then again, and need to store the minimum cost. How much is it taking to reach, means to cover all the nodes, and then after from B we need to start and just take out the minimum cost. How much it is required to let's cover all the nodes. It's like a brute force approach, taking each and every node and starting the DFS from there. And after
You
that,
can do that. Yes, you can do that.
it's a brute force approach. Means.
It's in a brute force with a greedy kind of an approach. So you're not going for the greedy, you're going for all the kind of a spanning tree, and out of which is minimum that you're trying to take. Right. Yes, you can do that. Okay. Another simplest approach can be going greedy, right? You're trying to be optimal. So you're trying finding out all, and out of all, so like you are trying to find out all the possibilities, and then you're trying to keep the minimum one. There can be a greedy approach as well. So let's think about it, that is the greedy approach will work over here or not. Okay, so I'll tell you that the greedy approach for both the minimum spanning or all any kind of minimum spanning tree is called Prim's and Kruskal. There are two different algorithms, Prim's and Kruskal's algorithm. They both are for minimum spanning tree and they both work on greedy approach. Optimized approach is also there, which you said, but it's very difficult to code, or it will be very lengthy to code. Okay, and so now we'll see the greedy approach. Will the greedy approach work? And if it works, how? Let's see that. The difference between these both is very simple. The Prim's and Kruskal's algorithms difference is very simple. They go with the same approach, greedy, but the difference between both is very simple, and which is that this one. The Prim's algorithm, we grow the spanning tree from the starting position. Then let's say you are choosing A, then you choose A, and from A to you'll go to the next node, which is having the least weight. Obviously it's undirected graph, so the direction won't be there, but wherever the least weight is there, you'll go, so that you try to cover as many as nodes with least weight. So let's say you have A to D, A to C, C to B, B to D to C, and C to B only, such kind of graph only. And you have some weights like this 1, 3, 5, 4, let's say 5, 2, something like that. So what you do, you go for first A to D because it has a minimum one. Okay, then from D to somewhere you'll go which is minimum one. So D to C you go with it because it has a minimum one. Now from C to B you go with minimum one. Now if you see, okay, let's say C to B you go with the minimum one. And then from B to C you go A, B, C, D, okay, E. And then B to C you go with the minimum one. So in this way you're trying to cover with the least possibilities, or the greedy approach kind of a thing. Then it's called a Prim's algorithm. Now the Kruskal's one will be a different way. We'll see both. I'm just giving a heads up kind of a thing. Let's see first in which way the Prim's and Kruskal's will work. Let's see. Okay, let's say this is the graph. What it means by Prim's is that you start from first node. Let's say starting node is A. You see whichever is a least weighted age which is associated with A. Then you can say, okay, A to D you can go with the least one. Then you'll go with that A to D, and you'll mark that, okay, A and D are visited one, or this age is visited one. Now you'll compare two things. What is that? A to D you went because it has an age 1. Now D to you have multiple options. D to C you can go with a 3 age. D to E you can go with 5 age, and there is one more option which is A to B you can go with 4 weight option. Which one will you choose? So as you are going greedy, you'll choose the weight which has the least one, because in both the cases you are choosing, or in all the cases you are going into the new node only. You are traversing a new node only. So any of the option you choose, it will give you a spanning tree only. Point is, which will result you in the minimum spanning tree. So because of the minimum one, we are going for the, it started. So because of the minimum only, you go for the age, which is minimum. Let's say if it would have been 2, then you would have gone for this one. If it would have been 2, you would have traversed the B. Okay, so we'll see that. So as from D to C, you have to traverse with the minimum. You'll traverse with that minimum. Now again, you will have many choices, such as you can go from A to B in 4 weight, B to, sorry, not B, D to E in 5 weight, and C to E in 6 weight. Which one will you choose? A to B. then you'll choose A to B. Then out of all the possible option, you'll choose this. So this has become your minimum spanning tree, which is like A to D, D to C, A to B, and B to E, with the weights as 1, 3, 4, and 1 as one of the spanning tree. And this is your minimum spanning tree. Got it? How to code it, we'll see.
I have one question.
Yeah.
Actually, here greedy approach works because we need to means cover all the nodes, right?
Yes.
Because many a times when you previously discussed questions, in that cases, DP, greedy
Yeah.
does.
Agree. I agree. I agree with your point. In many of the previous questions where the DP kind of an approach were there, the greedy approach didn't work because we wanted to go for optimal one. Here, optimal one itself is a greedy, or itself is a minimum one, right? So the point is, that's why I said it's an undirected graph. In an undirected graph only you can go with this kind of an approach. If it's in a directed graph, probably some other approach you will have to choose. Why? Because you have many edges, right? Point is, if you go for the least one every time and you keep marking all the nodes as visited, point is you will not stop until all the nodes are visited. That is first thing. Second thing is that every time you are choosing only the least possible option, so it will give you the minimum spanning tree, right? The phenomena or the logic behind that is that to reach to E, you have multiple options. Is if you see 1, 5, and 6. Out of all, whichever is the least that you are choosing. So it's not like that you just like on a dynamic programming approach, you see that just like that to reach to E, you have three option, but you check, okay, via D, is it minimum like A to E, which is like 5 plus 1, 6, or A to D to C to E, which is 6 plus 4, 10, or A to B to E, which is 4 plus 1, 5, which is the least one. You're not finding that and then saying that, okay, A to E is reachable with least 5. That's why optimality or dynamic programming kind of an approach is not needed over here. What you want to do is, with the least possibilities, you want to reach to E. And as there are many directions possible, as I said, you can reach to B via this graph as well, A to D, D to E, and E to B as well. But as we are always going for the minimum approach where each and every node is connected, there is no unconnected node, right? So the point is, you will cover that node with the least one. Why? Because that node would have been connected with some other node such that that node also, let's say the D. Okay, so that node also you are covering with the least possible weighted age only. So that's why this approach will always give you the minimum spanning tree. Got it? Because if I say that, oh, okay, to reach to B, there are multiple options, but you are choosing the option where it's already minimum, like A. Via A, it can be reached very easily with the least possible weight, 4. And let's say the graph is extended and this some other nodes are also there. Okay, let's say the graph is extended and some other nodes are also there. Then A is also the least weighted traversed so far, because if you see, like D is also traversed with the least weight, or E is also traversed with all out of all, which is the least weight. So if I choose to go, let's say node P via C, I know that the C has also been covered with the least possible weights only, and via reverse, C has also been traversed via the least possible age of D, and same way D has been traversed with least possible age of A. And that's why if I say that This is what the part of spanning tree. Yes, with a greedy approach, it will give you the spanning tree, minimum spanning tree. Got it?
Yes, sir.
So let's see its code. Okay. And before taking a code of the minimum spanning tree with the Kruskal, sorry, Prim's algorithm, I'll take a break. Okay, you guys cannot take a break because we'll code it with the adjacency list. Okay, so you guys need to give more attention to it, because the same kind of coding practice will be necessary for rest of the types of code as well. And graph is considered to be one of the little bit difficult in interviews for coding one. So you guys need to give some, attention over there. Once it is understood, you guys can code on your own, but just once you have to give a little bit of attention. Okay, so take a break. It's 11:11 in my watch, 11:12 actually. We'll be back by 11:17, say 4-5 minutes. Sure.
Sure, sir.
So 5 minutes break, and then we'll see the Kruskal's code. We'll see the Prim's code as well and its logic, and then we'll break. Okay. After Prim's Kruskal's code for today, tomorrow we'll see some interview questions which can be asked with the graph. Okay, so let's see the Prim's code for the same kind of an approach. So what is required right now for with us? So it's required that we keep the list of all the ages that we have or we can process. Like as I said, from A to B and D both you can go, but you chose to go D. Why? Because it has a least weight. Now once you go to D, you should have all the options, like as I said, A to B you can go with the 4, or D to E you can go with the 5 weight, or D to C you can go with the 3 weight. Out of this all three, you choose to go with the least one. So first thing is the requirement is that you should have all the possible ages where you can go. With all the nodes that you have traversed so far, you have traversed only A and D because you have taken only one age, A to D. So you have only traversed 2 nodes. Now out of these 2 nodes, whichever the age you can go or whichever the rest of the nodes you can go, you should have the list of all. That is first thing. Second thing, you are choosing the least weight out of it. And that is every time. And that is every time. So what kind of logic will be there which gives us or helps us in this one?
Thank you.
Sorry?
Priority queue.
Yes, one thing is priority queue. And we keep on pushing all the things into priority queue. Or second thing is that you keep, keep it sorted only, right? Both the things are there. We'll see with one, which is very easy, priority queue. So heap kind of a structure, as I wanted to discuss that, because every time you wanted the least one, as I said, either heap or a priority queue, both are the same, correct? And then we'll go further. So let's see the algorithm for that. A simple algorithm can be, you choose from any starting vertex, okay? And then you add the vertex that are adjacent to it. You find it out all the vertexes which are adjacent to it. You choose the age with the minimum weight among it, and you add it into MST. So MST is what minimum spanning tree is. Let's say you have some data structure where you are just adding that which nodes you have covered or which ages you have covered. Let's say you are just keeping the list of ages, because age is in a data structure with us or the object with us. So list of ages that you are keeping, that is minimum spanning tree. So somewhere we are just mentioning what is into minimum spanning tree. Okay. And then out of all possible ages, you are choosing the minimum one, right? So this can be the algorithm which we discussed. Now how to implement that? Let's see that. A simple thing can be, So we are first defining all the things. Okay. One thing is all the list of vertices. Okay. Uh, in minimum spanning tree, how it is used, I'll explain it later. Okay. We have the final result set. Okay. Now, how we are starting, that is the thing. Main thing which we need is a priority queue where I'm giving a pair of integer to integer. Now, what is that pair of integer to integer? That is age. So either you keep a data structure or the object of age, or if you have created like a pair, then also you can keep. So any kind of thing that you can put it into priority queue. So where how you are representing the graph, that in that way you have to create a priority queue in a simplistic way. Now, once the kind of data structures are defined, we'll see how can we code for it. So once the initialization is done, the queue has been defined, then we can start. So first I'm starting from the first node, 0. Okay, so instead of A, B, C, D and all, I'm just giving all the definition as 0 and all that things. Okay, and I'm keeping a pair of the node and the weight value. Node and the weight value. And then I'm starting that, okay, obviously the first node will be there into the result set. So that I'm adding, and its parent, I'm marking it as -1. So what I'm doing over here in a very easiest way is that after A, which node will come as in minimum spanning tree, that I'm defining. So after A, D will come. Let's say somewhere I'll define C. So C also has, let's say, the parent A like this. A to D also I'm going, and A to C also I'm going. So C's parent, I'll mark its index as A, something like that I'm doing. So initially the first node's parent I'm marking as -1. So in that representation one wise, I'm going, because it's an easy one via which I can, uh, with parent-child relationship kind of a thing, I can easily represent minimum spanning tree, because in minimum spanning tree, it will be always something like this. Let's say E and B, something like this. And if I explain you very simply, the number of nodes -1 will be the number of ages that will be always there. So each and every node will be connected with one age only. So you'll have one parent, one child relationship only. One child will have one parent, and one parent can have multiple child, that kind of relationship only. So that's why it's easy to represent minimum spanning tree with such kind of a data structure in easiest way. That's why I have chosen that one. Got it? Now we'll see what next to be done once the initialization or the starting of the first node has been done. So I have initialized it and I have started the first node. Now once I have added or I have marked that first node is 0, and from there I have to start, what I have to do, I have to iterate over the priority queue and find it out which age to pick up or which node to pick up, like that. So I'm going over the priority queue and I'm fetching the pair, which is the minimum one. And after that, I'm getting from the pair, I'm getting first its vertex and second its weight, which one to get. Once I have got both the things, which node to process further and which age to process further, I'll add that thing into resultant one, right? So let's say this is the age that I have to go, right? So that age I have added into adjacency list. Furthermore, once I have got that age, what I have to do, I have to process for rest of the priority queue as well. So until it is not empty, I have to process the same thing again and again. So that same thing I'm processing like this. For that age, for all the nodes and all the list of that node. So first I have extracted the node, and of all that node, all the adjacency list I have kept it. So let's say in priority queue, I had first node A, right? So I have taken A, and once I knew that, okay, I have to take this one, what I'm doing is I'm taking all of its edges and putting into adjacency list. And after that, I'll take out the minimum one, correct? So if it is already not part of minimum spanning tree, not visited already, then I'll process it further. Then I'll process it further. So first I got the age object out of this list, and then once I have got the age, which is the least one that I have to process further, what I'm doing, I'm finding that this age is between which source and which destination, A to D. I'm taking D again and pushing into the priority queue. Like in a priority queue, I had A first. Now then it should be D. Then I'll take all the nodes of A and D, or all the edges of A and D, and I'll take the minimum one and I'll process further. So that thing I have to do. So the same thing I'll do over here. What I'll do, I'll take its destination and I'll put it into, and the its age, this values I'll take, and I'll create a pair and I'll put it into the priority queue. So at every time I'll have that objects into priority queue. So something like this, A to D I have with one, something like this I'm doing after the A has been processed, and A to C also is there with a weight, let's say 4 is there. So this both thing with this code, I'm adding it. So what I'm doing, A first I have started processing. I've taken its list over here, all the adjacency list over here, A to D and A to C. Out of all the ages, I'm processing and I'm putting into priority queue. So before putting into priority queue, I'm creating a pair of the node ID, which is like D has some ID, right? Like A has 0, so D has some ID. So that node ID and its associated weight. So that object I'm creating, and I'm putting into the priority queue. Now, which one I'll choose first? Whichever has a least weight, whichever will have the least weight. Got it? So this is the thing that I'm doing with this code. Clear?
There was just one thing. Means, for example, you are standing on A, and if you're processing A at that time, means while processing A, you are finding its connection and then taking out the keys, and according to the keys, you are pushing it into the priority.
Yes. So initially, how I have started, like as A, I'm starting as the same code should go further again and again. What I did, A with the least age weight 0, I have added into the priority queue, and then I have started processing. That okay, A with 0 I have started. So to start from A, what I did is I created this object of A to A as in a 0, and I kept it into priority queue. Now first I'll take the object because it's in a least one and a single one. I'll understand that this should be the source, right? And then what I do, I'll add it into minimum spanning tree somewhere. I'll show you how again. And as the node A has been taken, I'll take all its edges over here. As I said, yeah, I have taken all its edges over here. Got it? After all of its edges have been taken, what I'm doing it, I'm checking if it's already not visited. Like A has A to D and A to C, which are not visited. If it's already not visited, create a pair and put it into the priority queue. So this is already popped out, and then this a priority queue I have created. This is what I'm doing over here. Okay. Now, what will happen? Thus, the same process will go on again and again. Obviously, with adding into the minimum spanning tree. But what I'm doing over here, let's say once out of this both, I choose one, which is like D. What will happen? Again, the same code will go on, right? The same code will go on. While priority queue is not empty, extract a pair which has the minimum one. So A, I have taken it up, then I'll choose the D, right? Like A to D1 wala pair, right? Then I'll take its vertex, which is like D, and all of its adjacency list, I'll find it out. So D2, how many you have? Like D2C and D2E. This both I'll find it out, right? So I have now D2C and D2E with expected weights like 2 and 5, let's say. Now I'll iterate over it both and I'll push it into the priority queue if this node C and E are not visited. So if they are the destinations are not visited, this both nodes, this both edges, I'm adding into the priority queue by creating the object of destination ID. C and E has some ID, so that destination ID and its weight. So now in priority queue, as A to D I have chosen, in priority queue I have A to C with weight 4, D to C with weight 3 or 2, whatever, and the next object will be D to E with object with weight 5. So these three things will be there into priority queue. Obviously, representation wise, it will be like A's ID is 0, so 0 to C's ID is something. So that I think I'm keeping the destinations only and the weight, right? So in that way, I'm processing the ages. Whichever is the least one, I'll again extract it with this code because I'll choose the least from the priority queue, the least one, and I'll process it. Got it? So in this way, I'm processing it. I'm taking its source, like C, I have taking it up the destination, taking its value, adding it into the priority queue, and then, sorry, adding it to the minimum spanning tree, and then again. So in this way, it has been written. Clear? It's a fairly simple one. Now, once I have got it that, okay, this one is the least one, right? What I have to do, I have to add it into, okay, so in the priority queue I have added, then what I have to do, I have to add those things into my result set. Okay, that this is the weight of the minimum spanning tree's age and what is the result set. So the result set, as I have defined it, something like this, that D is the destination which can be done or which can be traversed via A. So D's parent I'm fetching as extracted vertex, which is A over here, extracted. So this is the same code which is going on. I'm just writing down into the chunks. So extracted, where it is, yeah, extracted vertex was A, initially A. So extracted vertex I've added into that, and it's weighted, which I have found it out over here, that whatever the weight of that, the least one, that I have taken it up, and I'm marking it as a result set, that from A to D with least one you have to go. So this is your result set or minimum spanning tree. Got it? And then you can process it further. So then again, this for loop has been done. I'll go again and find it out the next adjacency node. Clear? So after that, your for loop, if, for, and while completes. So that is into 4 chunks. I have explained the first while loop, in which you get the least initially the priority queue with the least weight of the age. After that, you process it, start processing the destination of it. You create an age and you put it again into the priority queue, and whichever is the least one, you put it into the result set. And this if, this if, this if, this if, this for, and the previous while which is here. This all completes if 4 and while. And at the end, you just print the result set. So print is the function, again, print minimum spanning tree. We'll see how you can print that. But in this way, your code completes in just one while loop and one for loop. While loop over the priority queue, for loop over all the edges. Clear? Or should I explain it once more?
Yes, okay.
Okay, Harsh, Jose, Sumant?
Once explain, sir.
Yeah, sure.
Now all I joined.
Yeah, I'll explain it further once more. All the part of the code.
Just one thing. Do you have the IDEO link for this?
Probably I will have. Let me show you. I have coded it, but I will have the IDEO one link for it. I'll show you. Before that, I'll just explain once more. Okay. So what is the initialization? Initialization is that in priority queue, I have to start from the first node A. So I'm starting from the first node A with its least weight 0. Okay, because my priority queue has been defined over the weight of the pair. Okay, now second thing. So once I have added the A0 into priority queue, that means I have to start from the node A. Okay, got it. What is the next thing that I have to do? The next thing is that with A, you have multiple edges, A to D and A to C. What you need to do? You need to first find it out. First, you need to find it out that what is the source node of A? What is the source node of the edge, which is the least one, which is A? So first thing is that to find it out. Second thing is that you need to find it out all the edges of this one. And out of that, you have to pick up the one which is least one, right? And then you have to do the same process again and again. So let's say it has two edges, A to D and A to C. So that thing you have to put it, right? That you need to reach D via weight 1. So that thing you are adding into the priority queue, and you can reach to C via weight 4, right? So this thing you have to add. Now again, when while loop will happen, what you'll do, you'll choose the minimum one, and you'll say that, okay, via D, what are the edges which can be reachable? Let's say B is reachable via 5, and with 2, let's say C or E is reachable, let's say. So this both, again, you'll push it into the priority queue. That is what we are doing. So first thing is this initialization of A0. Second thing is that what you're doing, whichever is the least edge you have, you are taking its vertex. Let's say A you have taken, and all its list D and C, all of its adjacency list, you have to fetch it first. So all of its adjacency list, you have fetched it first, right? That is into list. Now, once you have both the list, like A is connected with D and C, what you have to do? You have to put those as an object, D and C with D1 and C4 into priority queue. So that is what you are doing. If the D and C are not visited, if they are marked as not visited, what you are doing? You are creating, so destination and new key as an await and thing you are creating, and you are creating it as an object. You're creating it as an object. Once it is created as an object, like D and C's object have been created, what you are doing, you're putting into the priority queue. Simple. You're putting into the priority queue. Clear? So we have just added this all into priority queue. Now the thing is that we have to process it. So what is the processing it? As we have extracted the D first with the least one, that I'm taking. What is the parent of D? A. So that I'm marking as result stat. And what is the least weight for it? 1. So that I'm just marking that you can reach A to D in minimum spanning tree with 1. So that I'm marking into result set. That's it. Got it? And then I'm moving it further, that with D, which all I can reachable. So once this code will be completed, like if loop and if loop will be there, what it will happen, I'll again go with while loop. I'll take out the minimum, which is D, and I'll start processing it further. What are the ages of D? I'll take it out. I'll process all the ages if its destination is not visited. And I'll create the object and I'll put it into the priority queue. That's it. And every time again, I'm choosing the minimum one from the priority queue, which is extracted value, extracted vertex. And I'm making the destination as this, that this destination can be reachable via this extracted vertex. Simple. Like A to D is reachable. Now, whichever is a minimum one. Now that I'm choosing D to 1, right? So D and these are removed from the objects. Then you have B with 5 in the priority queue and E with 2 in a priority queue. So you'll take, okay, 2 can be reachable with a priority queue E, and E is parent is D. That is what you are doing with this extracted vertex. That relationship you are doing. Clear? In a fairly simple one way. How to print the minimum spanning tree? You are just printing all the result set. So an object of result set, which is you are passing into the minimum spanning tree, and how you are printing it. Because it has an apparent child relationship, you are just printing all the nodes and its parents like this. So result set of I dot parent that you are printing, okay, and its weight you are printing. Got it? So for I equals to 1 to I less than all the vertices into the spanning tree, what you are printing into result set, whatever the index is, that index is, so like D's index is, let's say 4. Now we have kept like D can be reachable with one weight via A, and A's index is 0. So you have created a result set over here, like 0 is a parent of 4. That thing you have created. So that you think you are printing that result set of D index, let's say 4, and its parent and its weight. So you are printing like this, that D node is reachable via A with weight 4. That is what you are printing. Now C node is reachable via, let's say, B with 2 weight, something like that. So this kind of things you are printing. That's it. Because that is what you have stored into result set in a simplistic way. Clear? Now I'll see that if I have the link of this in IDEO1, and I'll share with you guys into WhatsApp. Okay, we'll quickly see just the understanding of data structures or the logic of Kruskal. So what is the Kruskal's algorithm's logic? The Kruskal's algorithm's logic is that instead of starting from the vertex itself, you are starting from the greedy approach in which you're taking the least weighted age only. So in Prim's algorithm, what you're doing, you're starting from the vertex, and then you're taking whichever the least age it has. Instead of that, what you do in Kruskal's algorithm, what you do is you take out all the ages and you take first with the least one, like A to B is the least one that you take, and you mark it as this is the part of minimum spanning tree. Then you take the next least one, which is B to E. And if B to E is unvisited, like destination is not visited, you mark it as B to E is also visited one. Now furthermore, which is the next vertex, which is age, which is having a least weight, C to D. Now C to D, are they visited? Source is not visited, destination is visited. So that's why go ahead and mark that, okay, so via C to D, this age is done via C to D, so that you have marked now all the vertices. If you see AB, BC, and CD and E, all the things. So now this is your minimum spanning tree. You complete the whole iteration over the all the ages, but you see, okay, A is done, yes, B is done, yes. So that means AB, Both are visited. So can you add this edge into minimum spanning tree? No. D and E, both the edges, both the nodes are added into minimum spanning tree so far. Yes, do not add this edge into minimum spanning tree. And the same with this. So at the end, you have minimum spanning tree as this one only. 1, 1, 4, and 3. Okay. So we are just iterating over it, but we will not add into minimum spanning tree. Got it? So in that way, you can process all the nodes or all the spanning trees or the minimum spanning tree with the Kruskal. So the primary difference between both is, in one you are iterating from the or the starting from the node, and over here you are starting from the least weighted edge. Clear? Okay, its code we'll see tomorrow. I have it, but we'll see tomorrow. Otherwise it will be a little bit more for everyone to grasp. So we'll see it tomorrow. Or if you guys are fine with it, we can see right now.
Well, just one thing. Whatever manipulations that whatever thing that we have done for Prims, actually, for this, 1 minute. Actually, just wanted to ask one thing. For example, for Prims, what we used to do is we are standing on A and took its weight as 0, and then started from there. Means doing a DFS and then polling polling different nodes. Here
Yes.
exactly are we just iterating through all the nodes, collecting all the data, and then doing a priority queue on that?
No. So what we are doing is we have the graph representation with all the nodes and all the edges, right? So all the edges I'm adding into priority queue. So I got your point. What you are telling is that in previous algorithm, we had, so what I have is in graph, all the edges are there, right? When I'm creating it.
Right.
So this all the edges I'm directly putting into priority queue rather than starting from A and then adding whichever is the minimum one rather than starting from 0, right? And
Right.
then going with the least one, finding out that whichever is the least one, rather than finding whichever is the least one, what I'll do, I add everyone into priority queue so that the first object which I'll fetch will be the least weighted one, and then I'll start processing. Got it?
Okay. Means directly means instead of means adding it graph dot add edge, we'll be directly adding it in the priority queue, and then after we'll be taking out.
Exactly. So let's say in public static void main, you have the graph created. Then in the minimum spanning tree of the Kruskal's algorithm, what you do, you iterate over all the edges of graph and you push it into the priority queue, and then you start your logic. Or the same logic you can add it over here, and then you start your Kruskal's logic. Clear? Yeah, so both the things are fine, right? So if I explain, it will be very easy to understand once you have understood the logic. Only one thing we have missed over here, and that was this. If you see, with AB, we mark both A and B as visited. With B and E, we marked A, B, and E as visited. With C and D, we marked A, B, E, C, and D as visited. But is it a spanning tree? No. This is one part was left just after I finished my previous discussion. And where we are stopping is this, that as per logic, a minimum spanning tree should have covered all the nodes. So yeah, we have covered all the nodes. But first thing is that, are all the nodes have come as a destination? That is one thing. Why? Because a spanning tree, that means you are covering all the nodes. The second thing is that, how many number of edges have come into minimum spanning tree? So if you see so far, all the nodes have been covered, but so far how many edges have been come? 1, 2, and 3. As per logic, if there are 5 nodes, 4 edges should be there into spanning tree or minimum spanning tree as per mathematics, right? I have told you guys to figure it out. That was this part. So where we are missing, we have added only 3 edges. So the missing part is that the B So this is A to D, sorry. This is A to D. So D has come for the destination, E has come for the destination, and yeah, D to C, D to C. Okay, C is a destination, right? Okay, in whichever the way I have given. So C has come as a destination. Okay, so A itself is a starting node, so that we are not adding. But apart from that, which node has not come into the destination? B. So that thing we need to make sure that all the nodes except the starting node have come into destination. So that's why as the number of edges are also not n minus 1, n is the number of node minus 1, and also one node is also left processing into edge, though they both are covered as into this A, B, B, C, C, D. As this condition is not clear or not satisfied, we have to add AB as an edge into our minimum spanning tree, and now your minimum spanning tree is covered that each and every node are connected. So far it was disconnected. Why? Because how will you reach to B to E? You can reach to A to D with 1, D to C with 3, but how will you reach through B to E? No way to cover, right? So minimum spanning tree is connected one, and so for that you have to add this edge with the least one. So now each and every node is connected. A to D, A to B, then E is also connected via A or via B, and as well C is also connected via D. So all the nodes have connected. Number of nodes are 5. Number of nodes in age minimum spanning tree is 4. And now this is your final output of minimum spanning tree. Clear? Now how can we code for that? That we will see tomorrow. Okay?
Sure.
So officially our session is over today. Now Anurag has question. So Anurag, we can go through your question. I think you have some interview, so we'll discuss for that very quickly. I think people can stay. It will be beneficial for them as well. Yeah,
So
yeah,
the
Anurag. Yeah.
it's not yet finalized that I'll be getting a call, but I got a call from the HR, but I'm not sure whether she will be going ahead with the profile.
No,
But
no.
still, I
You have to be prepared. So it's for system design, right?
yes, I just wanted to have some idea about the system design. How should I be proceeding? As I'm having 4 years of experience.
Okay.
So
When is your interview? Let's say if it will be there, probably by when your interview will be there.
it might be for the first round, they will be sending me a link of a Hacker Earth, and then
No, no, no,
after.
no. No, for system design, they won't send you Hacker Earth.
Okay, no. For the interview means for the just for selecting for the first round, they will be
Acha,
sending.
got it. Got it. So your all the rounds have been not done, not completed yet, right?
It's just a start, means not even started. So
Okay, no worries. So okay, no worries. So you can ask the HR whenever the first round you do that when will be. Let's say if it is, then when it will be. Okay, accordingly we can plan. Why? Because let's say if it is after our schedule of system design, then I'll share you my previous batch video so that you can go through once again. Just for that, because it is around 6 to 7 hours, around 6 hours videos. Okay, that is first thing. Second thing, I'll give you heads up right away that in which way you can prepare for all. Okay, obviously Hacker Earth, you know, right?
yes,
In which way to code and all that things. Yes, you might be doing some practices as well, but yeah, it's fine sometimes if you know taken a help of some other guy as well who is logged in with you, or you are checking code somewhere. But just make sure that you write properly your code only. Just see the logic if you are not getting it. Okay, because mostly Hacker Earth codes will be such a way that its code will be somewhere with some other data structure. So see the logic and try to implement into your own way. That is first thing for Hacker Earth. Second thing, for data structures and algorithm round, it will be easy one. Amazon and Flipkart, Walmart all have started with easy, little bit easy for SD2 system, data structures and algorithm questions. probably 2D metrics and backtracking would be the toughest one for you guys. You will be for SD2, okay? You will be given interview for SD2. So
Dhaval, sorry to interrupt. So what,
yeah.
I've got 7 years of experience, and just in case if I'm applying, what level would I be?
So it depends with the company. Walmart SD3,
Okay.
Microsoft SD2, 62 level.
Okay.
Okay, Amazon SD2 or SD3. If you're going for SD3, they will take a very difficult interview. Instead of that, if you are going for SD2 and then after 1 year you think for promotion, then it will be easy. But
Okay.
like it's always like this: 2 to 10 years, or sorry, 3 to 10 years is as Amazon's tenure for SD2, and SD2 to SD3 people generally go. So let's say if you have joined Amazon as an SD1 from the college itself, or after 1 or 2 years of experience,
Yeah.
people will transit from SD2 to SD3 after 4 to 5 years of experience. Like SD3, there is like a team level architect who has 4 or 5 teams, and he has to choose, like, or under a director, one SD3 or two SD3 will be there who will take care of all the architects of all the 4 or 5 teams under one director. Okay, so that kind of role an SD3 will have in Amazon. So it will not be a lead kind of role. It will be pure a team architect level role, SD3. So up to 2 to 10 years of experience, they will consider you for SD2 only. Okay,
Okay.
and then for so DS wise, it will be easy. Probably no DP questions will be there. Probably, okay. Generally, tree, try, recursion, heap is their favorite. So based upon that, they will take. And obviously, based upon the team, interview level can be a little bit difficult. I think I have mentioned it, that if you're going for the Prime's team, it's a little bit difficult interview. If you're going for some team in which they are creating an internal tools for internal teams only, it will be a little bit easy. Okay, so difficulty level can be based upon that. But yeah, I have seen that for system SD2, they are not asking DP level questions as far as my experience. Now, third thing, system design. What to take care into system design? They will ask everything, low level design and high level design. And if it is Amazon, then Amazon principles. If it is any other company, then similar to Amazon's principle questions will be there, that I have seen that people have started. Even in Microsoft and Walmart, their principles are different, but the beneath logic will be always same. Okay, and they are asking the questions on that. So on these 3 things, you will be judged for rest of the rounds after system designs 2 round. And that, what are the things that you need to take care? In low level, how you are designing your DB. Whether it's you are making it as, what you can say, transactional database, how you are maintaining transactional things, non-transactional things, how you are making it and defining it. So how you are defining SQL and how you are defining NoSQL tables or structures, that thing they will see, and how it is much more optimized. I give you one example, just a very quick example, and probably the same thing I'll cover it into my system design round as well. Let's say you have to design a Google Calendar for sending an invite, right? Event invite or meeting kind of a thing. How your database thing will look like. So initially, if you think it will be something like this, that the person who has created it, so person ID who has created it, and invitee IDs, okay, in a table. So these are the list of invite IDs. Now, if you do the normalization, it will be like one person, let's say person number ID 1 and invitee ID 2, person ID 1, invitee ID 3, person ID 1, invitee ID 4, and event ID. So event ID, let's say X is the event ID. So for one X event ID, 2, 3, and 4 are invited by person number 1. So this is your normalized table. Now, what will be the structure for event? So event will have name, event will have description, event will have the person who has created it, the table of this or the link of this, or all the things that you can put. How will you keep the timings? That is what will be important over here. Let's say you say, okay, start time and end time, I'll keep it over here. Do you think it's optimal? Why? Because they will see, okay, if I have to query that what are my events for today? How can I find it out? Do I query on start date and end date? No. Why? Because just like our friend Harsh is there in UK, his dates would be like this for our 10 to 12 class. So for India, my 10 to 12 event is like this, but for him, it will be like probably 12 to 2 or 11 to 1.3, something like that, right? So the dates will be different. So how will you make sure that this kind of thing is happening? Because for him, if you do query, okay, the same event should be showing for yesterday and the same event should be showing for tomorrow as well, right? So with this kind of a start date and end date, how will you make sure that this query is optimized one? Because if normally if you do, this query is huge. Just think about it. So how will you do this kind of, how will you solve this kind of problem? So whenever you choose a database design, think about all the types of questions in your mind. That okay, if I have to represent it, or if I have to create an API on that, this kind of an API, what kind of query I'll create? That is what they will give most emphasis on. Second thing is that which kind of API you are thinking, because if you have an experience in REST design or microservices, they will see which kind of API structure you are creating. Okay, because with the help of microservices, it's in a different kind of API services. If it's a monolithic, it's even if it's not monolithic, it's a microservice based only, but each and every components are monolithic. Then also the architecture, it will be different. So which kind of API design you are doing? Are you using any API standards? Because if you create a different API with different logic, then are you creating any standardization or not? So there are few standardization like YML or YAML, YAML, some kind of standardization process is there. If you're using it, you can say, okay, I'm using it. Otherwise you can say no. So are you using that standardization process? Are you using the versions of all the APIs? Because somewhere it will happen that one type of logic is deprecated and you are writing a different kind of logic to do the same task, and you give the next version of it. So are you exposing that? Okay, how are you using queues? So API is defining an API or designing an API is a part of LLD. Designing a database is part of LLD. How you're using queue and rest of the structures, other data structures like SQS queues or any other thing, that will be part of your high level design. Which are the kind of components that you're choosing? Let's say if you have to choose that you have to design an e-commerce website, which kind of components you will choose? For UI, it's in a different thing. Then for REST, let's say warehouse processing, it's a different component. For order management, it's a different component. Now in order management, OMS only or warehouse management system only, how many types of components you are choosing? Which kind of APIs each one will expose? How do they communicate between each other such that if the order is cancelled over here, it should reflect over here. So they should be reflecting via queue, something like that. So that kind of design, how you are making sure works, right? That you have to discuss with them, that which kind of event oriented architecture you will create, or a queue based event oriented architecture you will create, right? That kind of things you'll have to discuss with that guy. Proper person will ask you the questions in the same way. And this kind of thing you might have seen into your companies as well, that generally upstream system and downstream system are there. You either call their API or that you just create an object and you put it into the queue so that their queue listener will listen from that queue that, okay, this event has been generated, this event has been cancelled, right? So that logic you already will have into your mind, but you just have to apply for this interview questions. And if you have not read about it, do let me know. I'll give you some pointers to read about those, that these are the things. Just read about it and relate it with your company's work, that which kind of work you were doing so far, and or even if you have not worked upon it, which kind of architecture right now is there into your company that you need to check. Okay, like there can be a question like this, that okay, if you're using load balancers. Okay, so load balancer will have something like this, right? There is a load balancer and you have multiple servers, like let's say server 1, server 2, and server 3. A simple kind of an architecture can be there. Now let's say the person, let's say P1, has been logged in via load balancer and his first request went to S1. Okay, now let's say the S1 got busy or down. The next request he is sending goes to S2. Now, how do you make sure that authentication doesn't happen again? Authentication token has been passing to all the servers. Or will you keep the authentication at the load balancer itself? What kind of structure do you keep? Such kind of questions will be there. Basically, majorly they will see for the LLD only, low level design, DB design, and all the things, because these high level things will be coming with the more work into high level design, or if you are very much familiar with the concepts. So less emphasis on high level, but major emphasis will be on low level design. As I said, API designs, your DB design, these two things will be much more crucial. And if you want to practice, you can practice it in any way. Just think about it. How do I design Ola? How do I define Ola Shuttle? How do I design Ola Shuttle? How do I design, as I said, Google Calendar? How do I design the mail? How do I design MailChimp? You know that MailChimp servers are there, which sends the mail for all the promotions and all that things. Like you're selling something, and whatever the promotion comes, that hey, today is the sale event and this event and all that things, that comes via some of the servers. MailChimp servers are there, or some other servers are there. Which kind of design they would be using? Think about those. Think about their database design, and then you can process it. Let's say the rule engine. All you guys would be working with rule engine, right? Some rules are evaluated. Let's say the credit card systems are there. You are platinum member, then such kind of rule engine should work with you, because you should get 10% discount on every order. But the same rule engine should give some other amount for express credit card or some other credit card, right? So how your rule engine should be designed in terms of DB? Will it be SQL? It will be no SQL? How? There is no, and let me tell you, there is no correct answer for any DB design. And the simplest example is this: Netflix has been designed on NoSQL, while YouTube is on SQL. To be frank, MySQL. To be precise, it's on MySQL. Now, if you think about a YouTube or a Netflix system design, it will be huge and very complex in terms of DB as well. But how do they have modeled for MySQL such that they get the best result? And the same thing they have modeled within NoSQL such that they get the best result. Results are same, but how do you model it? That makes a difference, right? So it's not right that you should go for this only or this only, but how you are modeling it, that is more important. So you need to ask, you need to think about it. Okay, how do I design this part? How do I design that part? Right? That kind of things you need to keep on asking yourself. So in my lecture, we'll see this kind of questions, okay, and some low high level questions as well. But let's say before our questions, if you have to go through it, okay, I'll share you the link of my previous sessions so that you can go through it. Similar kind of questions only will take this time as well. Okay.
And one more thing, Dhaval, can you share me the links that you were talking about, like event driven and
Yeah, all the concepts, right? So yeah, I have the list of concepts. I'll send you, and you can just start reading about it from the Google. Obviously, I don't have the precise link for that, but the concepts that you need to read or need to understand, that I'll share it with you. Okay. Obviously, I'll share it with the WhatsApp group later on once I complete the system design. But the same thing, I'll share it with you early.
Sure.
And the main thing is that, okay, once you clear all these things, then we'll talk about the principles for which they discuss. Okay, that we will see. So after your first round, do let me know and we'll discuss on the principles. Because the same principles will be there for your system design rounds. So I'll discuss with you how to model those. Okay, and same things I'll cover it into my sessions, but later on. Okay. So to you, I'll give you gist if you have the interviews further quickly. Okay. So do let me know if you need any other help, and we'll try to cover it.
Thanks, sir.
Okay. And if you have this, once you clear the Hacker Earth round, do let me know, and then we'll take it further quickly. Okay. Okay. I'll stop my session and we'll meet tomorrow.